Alright, students, will be reviewing the topical practice section A for chapter 19 on nitrogen compounds. Right, so for question 1, we are focusing on the basicity of organic nitrogen compounds. Okay, so you were told that benzocaine has this phenylamine linkage or phenylamine parts as the structural features. It's commonly found in suntan lotions. Its structure can be shown below. So alongside you have compound A and B. So if we take a look at compound A, it is essentially without the phenyl ring. So this is a normal primary amine. Okay, so this is a normal primary amine. For compound B, if you look at this portion, this is actually an amide. Okay, so if you were to expand this out, it's actually an amide linkage. Okay, so I'm just going to write this NH C double bond O and then an ethyl group. Okay, so this is actually an amide. Okay, so as what we have learned in this chapter, amide essentially is neutral. Okay, then for benzocaine, the NH2 is bonded next or directly to the benzene ring. So with that coming into consideration, the lone pairs of electrons on nitrogen can partially delocalize into the phenyl ring. Okay, so although it's partially delocalized, it is still a stronger base than the amide. So benzocaine is expected to be a stronger base than B. Okay, so compound A is a primary amine. You have this huge group over here, this cyclohexyl group. It will partially donate its electron density towards NH2, so the lone pair electron density on nitrogen will be enhanced. Okay, so you would expect it to be a stronger base as compared to benzocaine. Right, so question is, we're supposed to arrange benzocaine, compound A and B in order of increasing pKb. So let's focus on what we learned in acid-base equilibrium. Increasing pKb means from the lowest, okay, to the highest. Okay, so that also means that we are arranging them from the strongest base to the weakest base. Okay, so with that coming into consideration, we are expecting the weakest base to therefore be B. Okay, because B essentially is not a base, it's neutral. So again, lone pairs of electrons delocalize okay, across the CO pi framework. Yeah, so the bulk of the electron density is actually delocalized into the carbonyl oxygen. Strongest base therefore is A. Okay, because for A, the electron density of the lone pairs of electrons on nitrogen is enhanced by the electron donating nature of the cyclohexyl groups. Okay, then benzocaine will be somewhere in the middle, so I'm going to write it in the middle. Benzocaine. Yeah, for benzocaine is somewhere in the middle. The reason being the lone pairs of electrons is partially delocalized into the phenyl ring, so it makes it less available to coordinate to a H plus or to a Lewis acid as compared to that of compound A. Okay, then for compound B, not available at all because the lone pairs of electrons is largely delocalized across the CO pi system. So therefore it can't act as a base. So if it were to act as a base, it will take on a positive formal charge or a +1 charge, and this +1 charge is actually detrimental. Yeah, because imagine if this has a +1 charge, so I'm just going to write a hypothetical situation here. If this were to be a +1 charged, all hell is going to break loose because this is an electron withdrawing group. Electron density will be withdrawn towards the nitrogen with a plus charge. Yeah, so it's making the situation worse, destabilizing the whole system. So it's definitely not available to donate, because if you were to donate, then you would take on a +1 charge, formal charge or real charge. It is both, and then CO will delocalize electron density away from it. So it's a double whammy. Okay, right, so that's the order we're talking about. Okay, question 2, distinguishing test. So you're supposed to suggest a simple chemical test to distinguish between benzocaine and compound B. So again, benzocaine and compound B. Our focus will therefore be on phenylamine. Okay, what is the characteristic reaction of phenylamine that we learned in chapter 19? Yeah, so of course, based on our knowledge, aqueous bromine will be the one that we are looking at. Okay, because when you add aqueous bromine to benzocaine, you are expecting yellow-orange aqueous bromine to decolorized. Okay, so we're expecting for benzocaine, yellow, orange, bromine aqueous to decolorize. Okay, for compound B, remains yellow, orange. Alright, then I mean, as per requirements in your lecture notes, you were also told that you are expecting a white PPT to appear. Yeah, but as I mentioned in the lecture videos on phenols as well as phenolamine, right, you might not see the white PPT because essentially the white PPT you observe is the addition of aqueous bromine to a pure phenolamine where you generate 2,4,6-tribromo phenolamine. But in our case here, if you were to add aqueous bromine, you are generating a dibromo. And with this ester linkage, we are not sure if we are going to observe white PPT. So unless you have no choice, or you look at the marks given to you, if not, you might not want to write white PPT. Of course, if you want to, you can write white PPT appears. Okay, can so these are two observations: yellow, orange bromine decolorizes, white PPT appear. But as I mentioned countless times in my lecture videos on alcohols, chapter 16, and chapter 19 on nitrogen compounds, you might not observe the white PPT, especially in a humid, wet weather condition like that in Singapore. Right, okay, question 3. Supposed to construct a reaction scheme to prepare benzocaine from methylbenzene. Okay, stating the reagents and conditions for each step. So let us do a bit of an analysis, right? So we want to produce benzocaine, so from methylbenzene. So methylbenzene looks like this. Okay, methylbenzene, and then multiple steps. We're going to get benzocaine H2N, and then and this is the ester linkage. Okay, like this. All right. So I think first of all we have to recognize that what are we going to introduce into the phenol ring. Okay, so we are going from a 1 substituted compound, which is methylbenzene, to a 1,4-disub. Okay, so first of all we need to think of a way to introduce NH2 into the system, and based on what we learned in arenes, it is not possible to introduce an NH2. Okay, so an NH2 precursor is usually a nitro group. Okay, so maybe introducing a nitro group will be a good strategy, and introducing a nitro group when I still have my methyl group is definitely a plus strategy. Yeah, because a methyl group is 2,4 directing. Okay, so that's the first thing we need to look at, and then now looking at this, we have an ester linkage. Okay, so for an ester linkage, if we were to look at a precursor of an ester linkage, we're actually looking at a carboxylic acid. So maybe I'll just draw a precursor out before that. So I'm going to have a carboxylic acid. Okay, so from a carboxylic acid to an ester, yeah, that is usually quite straightforward and easy, because from a carboxylic acid to an ester, I'm going to perform esterification. Okay, right, so that will probably be the strategy I'm looking at. So so I'm just going to draw the pink structure out. Just going to think of thought process. So from here to here, we're going to perform esterification. So we're going to have ethanol as well as corn sulfuric acids as the catalyst. So maybe we want to say a few drops, but maybe not necessary, so we just say heat. Yeah, so in the actual research lab, we heat it under reflux. Okay, actually one that probably will give you a better yield is to convert it to an acyl chloride, but we're going to run into a danger because we have a NH2 over here. Okay, so that is probably something that we want to look at. Okay, we're not saying this is the definite answer, but it's something that we can maybe look at when we begin synthesis. Okay, so earlier on I mentioned that in order to get the NH2 out, we need to convert it to introduce a nitro group. So in order to introduce a nitro group, we are looking at a reaction that we are familiar with. Okay, we're going to use corn sulfuric acids, corn nitric acids, Okay, and then do we need the heats? We don't have the heats because if you look at our new curriculum, we have a methyl benzene, right? Methyl group is an electron donating group, so you activate the benzene ring towards electrophilic substitution. So room temperature condition is likely to be suffice. So we can write maintains at RT or 30 degrees Celsius. Okay, so I'm just going to draw the structure out. So you have phenol ring, methyl group, as well as a NO2. Okay, right, then from here, I think what we're going to do next is we're going to reduce the NO2 into NH2. Okay, so we're going to use the usual condition that we learned. So tin in con HCl and then heat. Okay, so we're going to, because we have not added any base, so we're expecting my NH2 to be protonated. So NH3 plus and then a CH3 group. Okay, then from here I'm going to perform side chain oxidation. So I'm going to oxidize my side chain to the benzoic acids. Okay, so I'm going to, okay, so I think from here I should be able to get this straight away. So I'm going to oxidize the side chain to benzoic acid. So the side chain oxidation, I will need to use KMN for potassium permanganate in sulfuric acids, and then I need to heat it. And with that coming into the picture, then I'm not going to expect this to remain deprotonated, so it will be protonated. So I'm going to just draw it out, H3N plus. Okay, and because it remains protonated, maybe the first thing that we probably need to do after we perform the esterification is to get rid of the acid or get rid of the protons on NH2. Yeah, so I'm just going to modify this a little bit. So I'm going to erase this. Okay, so what I'm going to write here, I'll write in orange. So first of all, the usual condition, I'm going to use ethanol with corn sulfuric acids, heat. Okay, then the second step, I'm going to add in cold sodium hydroxide. So I just put cold sodium hydroxide. The cold sodium hydroxide's purpose is really to deprotonate the protonated phenylamine as well as remove any excess acid that is present. Okay, so with that, you notice that the strategy towards working on synthesis is really to look at how, or rather, it's easier if you are able to draw in your final products as well as your starting material, and then you try to go one step back from your products and then one step forward from the starting material. Usually that will get you somewhere, and then from there then you can easily try to fit in the jigsaw puzzle and then get the final synthetic rods. Okay, so we're going to move on to question 4 next.
For question 4, right? For this particular question, it's kind of like a synthesis questions. But of course, you are given the intermediates, or you are given the starting material, you are given the final products, and you are supposed to find out what the intermediate is. Okay, and you are given this substrate, which is a ether that you are not very familiar with. That is why they actually gave you this particular clue that the reactivity of propoxybenzene is similar to that of phenol. Okay, you need this particular clue to help you to look at the directing effects. Okay, so I will just straight away go into ChemDraw so that we can get the structures out. Okay, so I copied the questions over here. Okay, so in case you're not aware, the directing effect, as mentioned last year, they are all in your data booklet. So I will just go straight into your data booklet. Okay, they are all given here. So it's a little bit of revision for you in case you are not so aware of it. So the nature of the directing effect is due to the nature of the group. Okay, whether is it donating or withdrawing groups. But there are certain withdrawing groups, especially the halogens, right? They are withdrawing, but the directing effect is to the second and the fourth position. And then the reason is actually given in your lecture notes under the extension section. Okay. Take note that your data booklet does not tell you about the strength of the donating group. Okay, so for example, you are probably aware that LQ groups are weakly donating. Okay, however, groups like OH and NH2, they are strongly donating because the lone pairs of electrons on O and N partially delocalize into the phenol ring. Okay, this information is not provided in the data booklet. So you have to know that from your theory in your lectures. Okay, so please be aware of that. And the nature of deactivating groups, right? Okay, usually halogens are weakly deactivating. And if you scrutinize these deactivating groups, right, you realize they have something in common. These four has the C double bond O. Okay, so there are carbonyl groups. So carbonyl groups are strongly withdrawing. Okay, as you may be aware of. And then another one is nitro. Nitro is withdrawing due to the N double bond O, and then CN is due to the C triple bond N. So C triple bond N is actually quite similar to C double bond O. Okay, so usually we say that CN group is a masked form of a carbonyl group. There's a special one that maybe is not very apparent in your curriculum. That is the ammonium lah. You realize that NH2, right, is donating, but ammonium is withdrawing. For a very simple reason, once the lone pairs of electrons get protonated, it will no longer be able to delocalize into the phenol ring. So eventually, the positive formal charge on nitrogen, right, will result in a overall withdrawing effect. Okay, so please take note of this because this will help you to solve some of the questions later on. I think especially question 7. Okay, so with this in mind, then we'll look at the question. So if you were to take a look at this particular structure, which is R, I'm just going to paste it over. Okay, if you look at the fact that the propoxy group is actually similar to OH, right? Okay, then you would actually expect a tri-substitution to take place if you were to add bromine. Okay, you notice my last qualifying statement. If you were to add bromine. So if you add bromine, bromine will go into here, here, and here. Okay. Now, you are probably not aware that actually the bromination does not occur at the same time. It's actually stepwise. Okay, so if you look at probability, these three groups, these two groups will have a greater chance because getting the second position in, you have twice greater probability as compared to this. But in terms of steric, this is actually further away. Okay, so if you look at a simple prediction, you expect bromination to take place at the 4th position first. Okay, the next question that we usually will ask ourselves is, if the bromination will take place at the 4th position, like, how will the bromine affect the overall substitution pattern later on? Okay, well, I mean, that's a valid question, but you are probably aware of what I mentioned earlier on. The bromo group is weakly withdrawing, but the OH or the O-alkoxy group is strongly donating. So normally when it comes to this kind of situation, you would expect the strongly donating group to actually dominate. Yeah, and that is why if you subject R to bromination condition, right, you will get the 2,4,6 product quite easily. Okay, so you will actually end up with the 2,4,6 product like this. Okay, without any of the bromine affecting one another's substitution pattern later on. Okay, so this is pretty straightforward, and you have learned this under phenol. Okay, however, the situation is a little bit different here. Okay, so now I will go straight into the question. Okay, just now I wasn't really exactly answering the question directly. So if I were to go straight into the question, right, you realize that they want you to synthesize T from R. Okay, so in that sense, the first thing to look at is what is the substituent pattern of T of the two additional substituent with respect to the O-alkoxy group. So in that case, they are actually second and fourth position. And from earlier examples and even from the chapter on aromatic chemistry, right, you realize that you cannot introduce NH2. You can only introduce NO2. So only nitration works. Okay, so if only nitration works, so our next consideration would then be how will the nitration take place? Okay, so I think without actually much consideration and from what you heard earlier on, you probably expect the first nitration to take place at the fourth position, like this. Okay, now when this happens, right, something interesting, there's some interesting changes to the system. Okay, so the interesting change would be if I have a nitration taking place at the fourth position, the next question to ask ourselves is, right, will the next nitration take place easily? Okay, so well, as I mentioned earlier on, right, NO2 is a strongly withdrawing group, O-alkoxy is a strongly donating group. So it's kind of like you have a system where you have the two groups coming in together, right, and then they kind of neutralize, even the comma, neutralize each other's effect. So in that case, your benzene ring or your phenol ring is back to square one. Okay, it's as though this compound is like a benzene ring, but of course, that is inverted comma, just a very loose way of simplifying things. Because at this stage, you don't know whether O-alkoxy's donating effect is maybe slightly stronger or slightly weaker than the withdrawing effect of NO2, but that is not important. And you can actually study that. Okay, you can actually go through a study on that. But again, this is a H2 kind of question for assessment's sake. I mean, there isn't a need to go a lot into details. Okay, but at least you know what I'm trying to say when I say that each other kind of, like I withdraw, you donate, so the overall electron density of the phenol ring is now reduced pretty drastically. Okay, not as much as before. So in that case, can the second nitration take place? So my answer to you would be definitely yes. Because of course the question is, can you nitrate a benzene ring? You can give me a very simple answer. Obviously you can nitrate a benzene ring, right? Use corn sulfuric acid, corn nitric acid. So yes, after the first nitration take place, the second one can take place as well. Okay, I wouldn't foresee it as a big issue, and that is why this question is sort of valid. Okay, because the next question that you might ask yourself is, can I have the third nitration here? So obviously no. Okay, very difficult. It's not no. It's very difficult. You need special condition. The third nitration will be extremely difficult because I have two withdrawing group versus one strongly donating group. The overall electron density of the phenol ring is reduced drastically. So if I want the third nitration to take place, I need very drastic condition. Okay, so in that case, I think you can very easily, or you should kind of be convinced. I hope that your S, the structure of S, okay, is the one in blue. Okay, so I'll just going to put it in. Okay, so I hope that this is okay. Okay, and as I mentioned earlier on, if you have a O-alkoxy nitration is simply dilute nitric acid, I think you can easily get that condition. But now, are you aware that you need a second nitration to go in? Okay, so if you need a second nitration to take place, then my suggestion is just use the condition that you are familiar with. Con H2SO4, con nitric acid, and then heat under reflux. Okay, you probably do not need to be worried about whether you're going to get a third nitration. Okay, because the truth is extremely difficult under thermal conditions. Okay. You also don't need to worry whether it will stop at 1, because I think I've explained to you earlier on. If you want to start at 1, you don't use this condition. Okay. Yeah. Now, the difficulty about this question and the controversy about this question back in 2008 or 2009, when it was first set in Cambridge exam, is how do you do the reduction of NO2? Like, how are you going to perform the reduction? We call that selective reduction. Okay, that is difficult. Okay, that is difficult. But you have to bite the bullet, because the question is as it is. You get my point, right? As in, whatever you propose here, in that sense, it must work, and you only know of one solution. To be honest, you only know one solution. And what is the solution that you're aware of? On HCl, I guess. And then with tin. And then again, heat under reflux. This is the only condition you're familiar with. Okay. But the question, of course, you have in mind is, if I put this, right, then wouldn't both be reduced at the same time? Yeah, I mean, that is the predicament that the student face in this kind of question. But then there are a lot of issues behind the nature of this question. And of course, in the actual synthesis, tin in corn HCl isn't used entirely. They use something else. So if you want to sort of get around the problem, you might just want to put in a word limited here. Okay, you want a limited here in order to control the reduction. Okay, but of course, to tell you the truth, this is not the real condition that works. But we are just suggesting this because with all due respect, and you are not within what Cambridge requires you to know, and within what you know, right? This is the only thing you can give, at least at this stage. Okay, but not to forget, after you do the reduction, what happens to your NH2? It's actually protonated, right? Yeah, so you probably need cold sodium hydroxide. Okay, and this is a workup step. Okay, so I just put in the workup. You don't have to put in the workup. I say you don't need to put in the bracket workup. I just put that in just to remind you guys that this is actually a workup step. Okay, so this is the condition you use to reduce S to T. Okay, and some students in the past, some of the seniors in the past actually asked me why is it a sort of like a selective reduction at the second position. Well, I mean, a very simple answer I can give would be because of the tin, right? It's actually acts as a Lewis acid. So when the tin acts as a Lewis acid, right, it's able to coordinate between this lone pair in the O and the SN, and therefore deliver the H, okay, to the relevant position at the second position. Of course, it works here as well, okay, but the conversion of this is expected to be a bit faster. So it's kind of like a kinetic control here. But of course, all these not really in your curriculum, don't really have to worry about it. If it ever comes out in an exam, just bite the bullet and write something like this. I think that will be perfect. Okay, yep, and I think I talked a bit too much about this, but I think it's necessary because most of the time people ask a lot about this as well. The next part I'm going to talk about will be aspartame. Is a artificial sweetening agent used in soft drinks. Okay, so it's a very simple question. I will not go into details. Okay, so basically name functional groups. Okay, so I need to quicken up the pace a little bit here, so to catch up some time. Okay, so this is aspartame. Okay, now I'm just going to zoom a bit more. Okay, I'm sure you can easily tell me what are the functional group besides the phenol ring. What do you have here? Ester, right? COO. So this is ester. Okay. What do you have here? CONH. So this is a amide. Okay. What do you have here? Remember, two functional group, you need to tell me primary or secondary or tertiary. So this is one of them. So this is a primary amine. Okay. And then the final one here will be a carboxylic acid. So this question will be quite trivial. And then the next part will be, again, not too tough. What happens if you add dilute hydrochloric acid? Okay, cold. The word is cold. Please remember this. There's a difference between cold and hot. When it's hot, right, hydrolysis may take place. When it's cold, hydrolysis will not take place. Okay? And only acid base. So when we have the word cold here, we are really dealing with the protonation of the primary amine. Okay, so I hope this is okay. Okay. Nothing else. Please don't hydrolyze because it's cold. Okay, unless they write hot. Okay, and nothing's going to happen to this. Remember, this is a carboxylic acid. Okay, some students, when they work on exams, they do it too fast and then they forget about stuff. Okay. Next thing is ethanol chloride. So again, for ethanol chloride, what is likely to take place? So again, for ethanol chloride, it doesn't react with ester, it doesn't react with amide, carboxylic acid, no. So only the primary amine. Remember, ethanol chloride is often used to react with amine to give you amide. Okay, because carboxylic acid and amine doesn't give you amide. Okay, they give you the salts instead. Okay, so if you write that in, then this is probably what you are expecting lah. So you are going to expect the formation of the amides. Okay, can I think this should be fine. Okay, I think with this we are pretty much done with question 4. Okay, then we move on to question 5. Okay, so question 5 asks you to describe the reagents and conditions you need to do hydrolysis. So again, please make a decision. Okay, please make a decision. Meaning you want acidic or alkaline hydrolysis. The reason is it will affect how you draw your product over here. Okay, so if you want acidic hydrolysis, then you draw acidic hydrolysis products. If you want alkaline hydrolysis, then you draw alkaline hydrolysis products. Okay, so I don't think I need to tell you how you should be doing. If you want acidic hydrolysis, maybe HCl, heat under reflux. You want alkaline hydrolysis, sodium hydroxide, heat under reflux. Okay. Reduction of amide is in your current syllabus 9729. So they actually use a very, it's a reagent that you're familiar with, lithium aluminum hydride. Okay, in dry ether. Okay, this is the answer. Please don't heat. Heating doesn't work. Okay, so lithium aluminum hydride in dry ether. Okay, so the reduction will take place, and the reduction of amide and ester, the product is different. If you reduce amide, you get the amine back. Okay, just the amine, which means in short, you remove the C11O. If you reduce an ester, you get 2 alcohols. Okay, so each side gets an alcohol. Okay, so there's a difference in the product. Okay, anyway, let's do the hydrolysis first. Okay, so I've drawn it here, so we can. Okay, I'm going to zoom up. Okay, now, first we look at this. Okay, if you look at this particular system, right, it has interesting functional group that you are not aware of. So I've highlighted in red. Okay, this is not a functional group in your syllabus. Okay, it looks like amide, but it's not an amide. Okay, it's not an amide. Okay, however, it behaves similarly to amide because it seems to be like a diamide like that. Okay, so you have here and here. So you expect if you were to, okay, let's say we stick to acidic hydrolysis. So if we stick to acidic hydrolysis, you expect the amide to be cleaved here and here. Okay, these two parts. Okay, so if I were to draw the product out, okay, I'm going to cleave here, here. Okay, these two parts. Okay, and then after that, I'm just going to split them, and then I'm going to draw in the carboxylic acid. Okay. Remember, I mentioned just now, we are using acidic hydrolysis. Okay, but remember this. This is a hydrazine, and it has a lone pair. Okay, I mean hydrazine. If it's not familiar, then it's like amine lah. Okay, so there's a lone pair here. So you'll be protonated under acidic medium. So you should draw the protonated form. Okay, if you do it under acidic medium. Okay, so this will be your answer. If it undergoes acidic hydrolysis. Okay. What if it undergoes reduction? Okay. So for reduction, you simply just remove the C double bond O. And that's it. Okay, so this is the reduction product that I've drawn on the right. Okay. Yep. Okay, next we look at this phenobarbital. Okay. Okay, this is an interesting molecule because it has a lot of interesting, or rather, it has a series of interesting connecting function group I'm going to highlight to you. Okay, so this is the part. See, this is an interesting function group. Okay, so again, you don't know this. Okay, it looks like amide. Again, Cambridge purposely said it this way lah. It looks like amide, but it's not amide. Okay. It has a very long name. Okay, but I can tell you that it is actually a urea derivative. Okay, because this part comes from urea. Okay, and obviously this part is a dicarboxylic acid. Okay, but not to forget, when you hydrolyze this, all your CN bonds get broken because they undergo amide-like kind of hydrolysis. So it gets broken here, 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 and here. Okay, so there are several spots that the thing can break. Okay, so if I were to just draw the product out under, again, as I mentioned, acidic hydrolysis. So I'm going to first cleave here and here. Okay, I'm going to cleave these two parts. First, I'm going to draw them out slowly. Okay, so you're going to get this dicarboxylic acid. Okay, so I think this is fine. But not to forget, this urea, right? The CN will cleave also. So I'm going to cleave here. Okay, just going to cleave here and here. Okay. We have two ammonia. Not going to draw both, so I'm going to cancel one. And acidic condition, ammonia will exist as ammonium. And then obviously this is not going to be naked like this. So this should exist as CO2. Okay, right. So remember this. Acidic medium, you get CO2. Alkaline medium, you either get carbonate or bicarbonate. Okay. Don't draw both. Okay. So you decide acidic or alkaline. Then you draw accordingly. Okay. Yep. And if I were to do reduction using lithium aluminum hydrogen dry ether, what am I going to get? So again, you remove the C double bond O. Okay, so this is the product that you're going to get. Okay, at the end of the day. Okay, yep. And I guess that's it for question 5. Okay, yeah, this was a Cambridge question as well. Okay. Okay, next question 6. Okay, so question 6, I need to maybe we discuss it over here first. Then after that, we'll go into the details. Okay, so it's actually about a reaction that is not in your syllabus, but they provided you in the context of the question. So it's about a German chemist, this Hoffman, not the Royal Hoffman, not the Nobel laureate. This is someone else, long before the Nobel laureate Hoffman. Okay, so discovered that if I treat a primary amide with aqueous alkaline bromine, I produce primary amine with one less carbon. Okay, there is a new term here, but people please don't be alarmed. Primary amide. Okay, as I mentioned, you only need to label your function group as primary, secondary, or tertiary for alcohols and amines. Okay, anything beyond that, like amide, all this, don't need. So this is just a context for you. Don't get too worried about the terms. Anyway, if you don't know the term, it doesn't matter as well. It won't affect anything. Anyway, this is the overall equation. Okay, and then the details is given here because it actually goes through several stages. Okay, then I will go into ChemDraw now. I think it's easier to discuss from there. Let me try to remember the question. So first they ask you to construct balance equation. Then ask you to calculate oxidation state, reduce number of electrons on D lah, and then state other products. Okay, so I will just go straight into the. Okay, first, if I were to look at this amide, okay, at bromine I get this. So maybe let me draw it out first. It might be easier. Okay, yep. The drawing takes a bit of time. And then I'm going to draw A out. A is essentially you're replacing one of the H with BR. Okay, now if I just simply going by common sense, actually this was a Cambridge question as well. So let's say if we are to use common sense, what do you think is the byproduct? The byproduct. Okay. Now, I mean I think if I look at it in using in that sense common sense, right? N and H, there's an electronegativity difference between the two. Okay, I think you have agree with me on that. So if there's an electronegativity difference between the two, right, your H is likely as a byproduct, right, to be lost as something with a positive oxidation state. Okay, and then the other Br, if it were to be bonded to the H, right, then it has to take on the opposite oxidation state that is negative. So the most likely answer that you can give here will be HBr. If you were to agree with me on that lah. Yeah. Okay. I mean, simply by using some chemical common sense, you should be able to come up with the answer HBr here. Okay, but I attempt to actually give you a little bit more details, like looking at oxidation state changes, etc. And this is actually followed by a question later that they ask you what is the oxidation state of the bromine in A. Most of the students will give the answer as -1 because, you know, like bromine, halogen always minus, right? But if you heard me just now, right, it is not likely to be minus, it's likely to be +1, right? Just by a very simple reasoning that bromine is less electronegative than nitrogen. So again, if you assume a perfect ionic model, where the shared electron pair goes to the more electronegative element, you realize that bromine will only have 6 electrons around it. That is its 3 lone pairs. And therefore, you will have 1 less electron as compared to when it is in the native states, which is 7. So it has an oxidation state of +1. Okay, so I hope this does help you to go through, to go beyond the fact that bromine or halogen must always be -1. It really depends on the partner. The next part is more interesting. They ask you for the number of electrons around B, right? Let me see. Is it deduce number? Yes, deduce number of electrons around B. Okay, so to answer this question simply, right, I need to draw the dot and cross. Not that I love to, but I think it does help in problem solving. Okay, so when I draw the dot and cross, I'm definitely not going to draw the full dot and cross. Okay, it's just going to be a partial one where you get what you need to observe. Okay, so I'm just going to draw it like this. And then to ensure that it has 2 more. Okay, and then I need to put in the crosses. And just the crosses here, and then the crosses here, and then the elements H and Br. Okay. And then I think it does help wonderfully if I can put in all the crosses for the Br. Okay, and then obviously zooming in even more helps. Alright, and let me just remove all the red stuff, all the warnings. Okay, so that you can see. Okay, now, again, as I always mention, right, common sense help a lot in problem solving. So, in the process of getting B, right, okay, I'm just going to shift it like this. You eliminate HBr. Okay, remember this. So my question to you is, how are you going to eliminate HBr from here? Do you realize that there are 3 possibilities? There are 3 possibilities that you can eliminate HBr. Okay, meaning there are 3 ways. Okay, one way is both NBr and NH undergoes homolytic cleavage, like this. Okay. Now remember this, the condition doesn't change. The necessary condition for HBr to be formed. H and Br definitely 1 bonding electron pair. And then Br will have 3 lone pairs. You can't change that fact. Okay, you can't change that fact. You cannot just, H and Br only 1 electron between each other. No such thing. Okay, so with this idea in mind, right, if you look at N, right, how many electrons are there around N? So if you do a quick count, 6, right? 1, 2, 3, 4, and then this bonding electron pair, 5, 6. So 6 electrons around N. That makes perfect sense, right? Okay. Then some students will say that I'm biased. Say, oh, because I like homolytic cleavage, so I'm biased. Actually, if you realize, it doesn't matter what I like. Okay? If you don't like homolytic cleavage, you can have heterolytic cleavage. So in this case, like this, and then like this. Okay? And then you realize the outcome is the same. The outcome is the same. 6 electrons around N. Okay? The outcome is the same. Then if you don't like this, I can show you another one. Same outcome as well. Okay, say similar outcome. Okay, so like this, like this, like this, like this. Okay. So the outcome is the same. Still 6 electrons. So at the end of the day, no matter what you do, the number of electrons around N is 6. Okay. So then of course you ask me, so which is the actual pathway? As I said always, right, it's not important because you're not given any data to deduce the actual pathway. You are only given the data to ask you to suggest and make some prediction based on the information given. And these are important skills. So in that case, yes, 6 electrons around. And okay. Gonna zoom out. Okay. And the next part is they ask you for the, let me see, suggest the other product of stage 4 and hence construct a balanced equation. Okay, now zoom in a little bit. Stage 4. Okay, this interesting functional group, right, is called isocyanate. In case I Google this, okay, isocyanate. It's a very important functional group in the polymer industry. Then again, of course, the question is, why is it important, right? Okay, I'm just going to draw it out first. O, you have an N, and then you have a C, and then you have an R here. Okay, it is important, right? Because it is flanked by two, or rather the carbonyl-like carbons is flanked by two highly electronegative elements. Okay, N and O. That makes it quite unique. Okay, and it's often used for polymerization. You know your bowling ball, right? The poly is actually, there's a functional group called carbamate. Right? It's actually made from isocyanate and NH2. Okay, anyway, not important here. Anyway, okay, so you have CON, and then after that, okay, how do I predict what is the side product? Or what is the other product? Right? Again, we can simply make use of our chemistry knowledge. Okay, don't really need very profound chemistry knowledge here. Again, the idea is enough for me to do some prediction. Now, if I have a hydroxide, which is a nucleophile, and I have a NCO, and I tell you that the carbonyl carbon is electron deficient, right? The first thing that comes to your mind must be your carbonyl carbon will undergo nucleophilic attack, right? I mean, okay, again, I am treading on thin ice, whether is it out or in or syllabus. Actually, as I said, it's not very important at this stage, because what is important is how are you going to make use of the knowledge you have to help you solve the problem. Okay, so with this little idea in mind and with some ideas that you are able to do nucleophilic addition like mechanism, you can do something like this, right? Okay, the OH minus attacks the carbonyl carbon. And then what's going to happen next? What is going to happen next? Will the pi bond break towards the N or break towards the O? Of course, then go back to your basics. Is O more electronegative or N more electronegative? So, of course, the answer is O is more electronegative. So, it's likely to break towards the oxygen. So, if it breaks towards the oxygen, this is what you're going to expect, right? Right. Okay. Now, just allow me to complete, not complete the mechanism, don't worry. Okay, not to complete the mechanism, but just allow me to complete just draw the intermediate out for you. Okay, because I think it's there is value in drawing the intermediate out. Okay, so let me just okay. Okay. Okay, I think I'm missing something. Never mind. Let me just put the stuff in first. So OH here. So O minus. Okay. O minus. Okay, and then there's an N here. Oh, okay. So I know what I'm missing. Yeah. Sometimes the software is quite limited. Okay. Okay. Now, this is likely to be your intermediate. I mean, not say likely, like it is like the intermediate, right? Okay, so this is the intermediate, right? Okay, I'm not going to continue to draw the mechanism, but those of you doing H3, right, I think you should continue to see if you can get this, because it's, it's the kind of hydrolysis reaction that is quite commonly asked anyway. Okay, but for the rest of you, right, do you realize it doesn't matter whether you can draw the mechanism or not, because at the end of the day, you can make some meaningful prediction. Now, okay, I'm just going. Do you realize that this part, right, resembles this? Okay, resembles the RNH2. Okay, so there isn't a need for you to draw the mechanism, because at the end of the day, all you need to do is just to say, somehow, if I continue to draw, I will be able to get this, and therefore, are you able to make the intelligent guess that at the end of the day, this portion, right, is the byproduct? So what does this look like? A lot of people will say CO2. Okay, I think CO2 is a very common answer. But as I mentioned to you, is it possible for you to get CO2 in alkaline medium? Okay, is it possible for you to get CO2 in alkaline medium? So no, right? So in alkaline medium, you should get either carbonate or bicarbonate, right? So therefore, your byproduct is carbonate or bicarbonate, which means CO32 minus or HCO3 minus. Okay, so I'm just going to show you how I'm going to do the balancing equation. Okay, just a simple one. So R and CO. Just going to shift out. Yeah, R and CO. Okay, just a simple one, plus OH minus. Okay, so what product do you like? Okay, so okay, let's say you like bicarbonate lah. RNH2 plus HCO3 and minus. Okay, let's say you like this. Okay, if you look from the left to right, there's something else missing lah. Okay, now R is there, N is there. Okay, the H's. On the right, you have 3H. On the left, you have 1H. So 2 H's missing. On the left, you have 2 O's. On the right, you have 3 O's. So 1 oxygen missing. So obviously, the missing link here would be plus H2O. Okay? Yeah, so this is how you balance it. And therefore, I predict that my byproduct is bicarbonate. HCO3 minus. Okay, so I hope this is okay with all of you. Yeah, if you choose carbonate, which means CO32 minus, then I think on the left-hand side, it will be RnCO plus 2OH minus. Okay, so you just adjust your answer accordingly. Doesn't really matter. Okay, I think I've answered everything here. Yeah, so 6A is a bit, it's worth like discussing, because a lot of chemistry involved. And those of you, again, I mentioned just now, doing H3, you can seriously consider drawing from the isocyanate all the way to the RNH2 and then the hydrolysis products. Okay, I don't need to spend too much time on 4. Again, as I said, I mean, 4 is something that you guys are pretty good at as well. It's a one that you fill in reagents and conditions. Okay, so they said Hoffman reaction is used in the last step. Okay, and then suggest reagents from on 5, 6, 7, 8, and then structures C and D. Okay, so let me just go to the structures here. Oh, I need to zoom up. If not, it's too big. Okay, you notice they really give you the clue, right? They said that the last step is the Hoffman reaction, right? Okay, they kind of like mentioned that the last step is the Hoffman reaction. Okay, so in that case, you can easily tell me what your last compound is, I hope. Okay, it should be the amides, right? So I'm going to draw the amides. Okay, so your D is actually amide. And then how do you go from the acyl chloride to the amide? I think it's quite trivial. You just need ammonia. So I hope anything that's trivial, like I don't think I need to go a lot into details lah. Okay, because you can copy it from the notes. Okay, so we set up this part. And then I think to go from here to here, it wouldn't be too difficult as well lah. Because for 5, right, it undergoes bromination. And because I have an electron donating group, right, therefore my bromination, right, I don't need it to be in harsh condition. So basically just Br 2 R2 and Fe Er3. Okay. Room temperature will do, so no need to heat. Okay, because you have a donating group here. And then the next step, in order to you can see that the Br remains. So in order for you to get the acyl chloride here, your C therefore must be the carboxylic acid. Okay, so that's where you draw in your carboxylic acid. Okay, so if your C is the carboxylic acid, then of course your condition for 6 would be KMnO4. And then acidified with H2SO4. In that case, you need to heat under reflux. Okay, so you probably need to heat under reflux in order for the side chain oxidation to complete. Okay, and then of course your 7, okay, you need to convert to the acyl chloride, so PCl5. Okay, now people remember this. If you don't know whether is it solid, liquid, or even aqueous, don't put anything. But PCl5 is a solid. Aqueous will never work. If you put aqueous, it's straight away marked wrong. Okay, so PCl5 is a solid. Okay, so with that, I've completed question B. 6B.
Alright, finally we're looking at question 7. Okay, so for question 7A, you are given the formulae of 3 amino acids: glycine, proline, aspartic acids. Okay, question is to draw the displayed formula. Okay, so the focus here is on displayed formula of this particular tripeptide, glyproaspartic acid. Okay, so the question highlighted that you need to write it out in displayed formula. Okay, so therefore all the bonds must be shown. All the covalent bonds must be shown. Okay, so first of all, I have glycine on the left hand side. So remember, when you are writing out the formula for peptides, it must be written from the N to the C terminals. Okay, so now we have glycine first. So we have glycine over here and H2. Okay, so C will be H2 here, and then carboxylic acid. I'm not going to draw out the OH. Okay, so this will be linked to the secondary amine, okay, of proline. So this is a secondary amine. I'm going to highlight it in blue. This is a secondary amine. Okay, so maybe I should draw it in another color. Okay, so now if it's a secondary amines, I'm going to have an N here. Okay, I'm not going to draw the H because you're going to form a secondary amide. And then this is a CH. Okay, CH. And then I'm going to draw out the rest here. CH. Okay, so the irritating thing is I need to draw out the displayed formula. So everything has to be out. Displayed. H. Okay, then draw a bond here. And then again, I'm not going to draw the carboxylic acid. Okay, going to use another color, purple. Okay, so I'm going to link here. So this is NH and then CH, and then aspartic acid has a CH2 OH, or rather CH2 OH, double bond O OH. Okay, and then C double bond O and H. So the most common mistake that students can make when they do this kind of question is to not draw out the OH bond. Okay, so be aware of this. Okay, so this is the most common mistake that students can make, and that will give you 0. Okay, states the type of reaction undergone when forming the tripeptides. Okay, so again, we're expecting a reaction between carboxylic acid and NH2, definitely enzyme catalyzed. So this would be condensation because it leads to the production of a small molecule, in this case water. So condensation. Okay, describe the conditions needed to hydrolyze a protein non-enzymatically. So the keyword here is non-enzymatically. Okay, so we are expecting you to be using a strong acid or a strong base, but of course in a dilute version. So of course the answer is dilute H2SO4. Okay, or dilute sodium hydroxide, and then I'm going to heat it over several hours. So heat over several hours. The heating over several hours is really to ensure that all the amide linkages are hydrolyzed. Yeah, because if that is not happening, then you're going to expect quite a mess. Like you're not going to expect the formation of individual amino acids. It might lead to you having some dipeptides, some tripeptides, some tetrapeptides. So it's going to be quite messy. Okay, so really it depends on the purpose of what you want to do. Yeah, so in this case, question is just to hydrolyze a protein. So we assume it's a complete hydrolysis. So definitely we use strong acid or strong base and then heat it over several hours. Okay, next, we have the antibiotic valinomycin acts by allowing the uncontrolled movement of ions across cell membranes. So valinomycin is a cyclic compound containing 6 amino acids and 6 hydroxy acid residue. Okay, so question is, apart from the peptide groups, what other functional group is present? Okay, so perhaps I can just highlight those functional groups that are present. Okay, so besides the amide, the peptide linkages, so I have esters. Okay, so I have several esters. Okay, so I'm just going to highlight in orange. Okay, a couple of esters around. Okay, then of course I have LQ. So LQ might not be something you want to highlight, so just too much. So this LQ, this is LQ linkages, quite a bit of LQs here. Okay, so LQs. Okay, right. Okay, so another LQ here. Okay, then so the answer here will be, because the question asks what other functional group. Yeah, so what other functional group? So we're looking at esters. Okay, right. When treated with peptidase enzyme, the peptide linkage in the ring of the valinomycin are hydrolyzed, only 2 products are produced. Okay, draw the structure formula of 2 products. So this is only 2. Okay, so only 2 are produced. Okay, so I think we have to be a bit careful here. This peptidase enzyme, right, only hydrolyzes peptide linkages. Yeah, so with that coming into the picture, right, I'm just going to erase all this because you'll make my life, or rather our life, a bit easier to identify. Okay, so I'm just going to use a highlighter, very contrasting highlighter I'm going to use. Orange, okay. So my highlighter I'm going to introduce, I'm just going to sketch out the common ones. Okay, so I'm going to have this. Okay, like this. Okay, then just going to continue like this, like this. Okay, so this is a bit different. Okay, okay, wait. Okay, just going to highlight. Okay, sorry. I'll use similar ones for this because this is the methyl. Okay, and then okay, so the methyl I'll use the same color coding. Sorry. Oops. Okay, so there's something wrong with the, okay, so I'll do it quickly over here. Okay, so orange, okay, this is for, orange will be for this, okay, like that, okay, like this, okay, so that's orange, okay, like this, okay, so that's one, and then I have another one here, like this, okay, I think pretty much that's about it. Okay, then I'm gonna use another color for the methyl, okay, like this, okay, gonna use another color for the methyl, like this, okay, like this. Okay, then I'm gonna use green, okay, for this isopropyl, okay, so green will be like this, okay, like this, like this, okay, like this, and then like this. Alright, okay, so now you can see it's made out of 6 amino acids. So the one in greens are the amino acids, and then the one in orange and pink are the hydroxy acid. Okay, hydroxy acids. Okay, these are the hydroxy acid residue and the amino acid residues. Yeah, so question is, they are going to treat the valinomycin with peptidase enzyme, and then they said the peptide linkage is going to be hydrolyzed. Only 2 products are formed. Okay, so what am I going to do? So I'm going to simply just perform hydrolysis, okay, on the amide linkages. So I'm just going to cut here, the amide linkages, cut here, cut here, cut here, and cut here. Okay, what do you notice? Okay, so maybe I'm just going to box them up. So I'm just going to box it out like this, okay. Then okay, sorry, there's another amide here, I forgot. So like this, okay, like this, okay, like this, okay, and then like this, and then finally like this. Okay, I think from here is quite straightforward. What are the 2 products? The 2 products are, those are highlighted in green and orange, as well as green and pink. Okay, so with that, I'm going to draw them out. Okay, so I think color coding really makes our life easier. Okay, so I'm just going to draw it out. Maybe I'll just sketch it below here. Okay, so I think first of all, I'm going to draw this. Okay, so I'm going to draw in the carboxylic acids. Don't care about the ester, alright, because the ester is not being hydrolyzed by the by the enzyme. Okay, so don't worry about that. Okay, so this is one of the products. Okay, then the other one will be this. Okay, so I'm just going to draw it out. Carboxylic acids. Okay, then like this. Okay, like this. Okay, right. Okay, so these are the 2 compounds that I'm looking at. Okay, so the difference is basically both have the ester linkage. Okay, the only difference is one of them have 2 isopropyl group, the other one has 1 isopropyl and 1 methyl group. Okay, yeah, so with that, we have come to the end of the review for chapter 19, nitrogen compounds, topical practice, section A.
Next, I'm going to go on to question 7, right? So question 7 actually just asks you, it's actually acid-base equilibrium extended. Okay, so basically they tell you that there are 3 pK associated with glutamic acids. Okay, so let me just go into glutamic acids here. So there are 3 pK value associated with it, 2.1, 4.1, and 9.1. Now, please remember this is the terminology of amino acids. Okay. Meaning, right, when we tell you the pK associated with blah blah, right? Okay, so I think you have done the exercise just now. Okay, you probably aware that um carboxylic acid remains as carboxylic acid lah. Okay, but for amino, right, it is actually the protonated form that we're talking about. I hope you will recognize this lah. It's actually the protonated form we're talking about. It's never the NH2 because you can't lose the H for NH2, right? Because an amino group pKa is about 30 plus. This is 9.5. Okay, so obviously it's not 30 plus. Okay. Then of course, another thing that you might want to take note of is actually which is the stronger acid. So obviously, carboxylic acid is a stronger acid than ammonium, because for carboxylic acid, the conjugate base, the negative charge on the carboxylate is resonance stabilized, right? It's delocalized into the C double bond O, or rather into the carbonyl oxygen. But for the ammonium, the positive charge is not stabilized by resonance. Okay, once you lose the H, the lone pairs of electrons is there, naked, okay, readily available to accept another proton. So again, when you compare the two, obviously carboxylate is a more stable conjugate base as compared to an amine. So if you look at the pKa's, right, I will definitely put the highest pKa, or rather I will probably associate the highest pKa to ammonium. What about the other two? Okay, so the other two needs an interesting discussion. So what's the interesting discussion we're going to have? A very short one would be just to compare the stability of conjugate base. Okay, so suppose this is the conjugate base and this is the conjugate base. So my question to you is, which is more stable, the top one or the bottom one? And if you remember what I mentioned to you here, okay, ammonium group when protonate, ammonia group when, amines when protonated is electron withdrawing. So is it better to have a withdrawing group nearer to the carboxylate or further away? So I think the answer is obvious lah. Okay, so this conjugate base is likely to be more stable than this. So therefore, the pKa associated with this should be 2.1. It should be the more acidic one. And the one associated with this should be 4.1. Then, with this idea in mind, you can easily answer this, right? The major species at the different pH. Okay, what is the major species at a different pH? Okay, so with this idea in mind, does it make sense that pH 1, which is way below 2.1, okay, everything will be protonated? Does it make sense? Everything will be protonated. Okay, so this is the major species at pH 1. Does it also make sense that at pH 3, okay, which is above 2.1 but below 4.1, this carboxylic acid will be deprotonated? Okay, then does it make sense that at pH 7, which is above 2.1 and 4.1, these two will be deprotonated? And then does it make final sense that at pH 11, which is again way above 9.5, everything will be deprotonated? Okay. Then, of course, if you recall me asking you all before, if I ask you for the major species at pH 2.1, will you be able to tell me that both of these are the major species at 2.1 because you have half of this and half of this? That is an important idea that you need to be aware of. Okay? Can? Yeah, but normally people won't ask you that. They'll just ask you something way above or way below. Okay? I'm going to use the final 1 minute to write the final equation for the Zwitter ionic form. And then how does it react with acid and alkaline when added separately? Okay, so first you need to identify the Zwitter ionic form. So the total charge of this is +1. The total charge of this is 0. The total charge of this is -1. The total charge of the one on the rightmost is -2. Okay, so the Zwitter ionic form is this. Okay, so this is a Zwitter ionic form. Okay, I'm going to add H plus, and then I'm going to add OH minus. Okay, so I hope it's quite trivial from here. Okay, when I add H plus, I will get back the carboxylic acid. Okay, when I add OH minus, the other carboxylic acid will be deprotonated. Okay, right? So I have answered the question on how to actually what equations to write, and I just have one last final thing to mention. For those of you with problem getting the form, right, the forms at the major pHs, right, you can actually use the Henderson-Hasselbalch equation. pH equals to pKa, okay, plus log concentration of A minus, the conjugate base, over the concentration of HA. Okay, you try to use this form. It does help. So basically, if you know your pKa of the strongest acid is 2.1, that will be 2.1. The pH you want is 1. And then after, if you take the ratio, right, you realize that at pH 1, right, this is actually the highest number, the higher number, because the ratio is greater than, or is less than 1. Or between 0 to 1, sorry. Yeah. Then at pH 3, you realize that you get more of the conjugate base. Okay, because if the pK is 2.1 and pH is 3, you will get 10 to the power of 0.3, which is a number greater than 1. And if it's a number greater than 1, that means the A minus has a greater number as compared to the HA. Okay, so I think you can leverage on this equation. But as I mentioned, you don't really need to go into that kind of details because you can simply just look at the numbers. Okay, with this, I'm done.